Hey guys, we are back with another session today. So today we'll be talking about the qualitative analysis of cations and anions and titrometric analysis, that is the practical chemistry part, right? So that is really important for the exam point of views, because I mean the questions majorly they ask from practical chemistry are like if to find a cation or to find an anion, and also about the volumetric analysis. So these questions are quite common in the competitive exams as well, like in all the competitive end of exams, maybe it be for IIT or maybe for the lower the other institutes too, like bits and all, right? So let's not waste our time and start doing our qualitative analysis. All right, so for cations, so we know, so we're talking about what? Qualitative analysis. Now in our chemistry, we know that we have two paths to our salts. One is cation and the other is anion, right? Now anions are quite less, like there are sulfates and then there are phosphates, right? Chlorides, bromides, iodides, then there are carbonates, right? Nitrate, then there is acetate and oxalate. So oxalate is this one and acetate is this one. These are the anions. There are no groupings on this part, but on the cations part there are groups. So we have like 5 groups, right? Group 1 to group 4, group 0 to group 4, sorry. So for group 0 we have ammonium. Group 1 we have silver cation, and then we have mercury cation. In group 2 we fall for arsenic. Then also there is mercury. So mercury, as you know, there are like mercurous and mercuric. There are 2 oxidation states. So it can be in group 1 as well as in group 2. Similarly, we have Pb, plumbum, right? It can be plumbous and plumbic. So again, they are in 2 groups. Alright. Similarly, so we have arsenic, we have tin. I'm sure you know the formulas, the chemical names, right? The elemental names. I'm sure you know the symbols. Please, if not, if you don't remember the symbols now, do them as early as possible, as soon as possible. All right. Okay. And then there is bismuth, and so on. We'll look up them. Copper. For group 3, we have zinc, nickel, cobalt, manganese, chromium, and so on. Similarly for group 4, we have barium, and then we have calcium, and then we have magnesium, right? So we have to have an analysis of all these compounds, all the cations and anions in these compounds. So we'll see one by one for the cations first and then for the anions, so that we understand how they are generally found out. So what is qualitative analysis? First of all, what are we talking about here? So if you are given a salt, an unknown compound, then how do you even find out that what is the compound made up of? To find that the nature, the chemical formula for the compound, we have to do the qualitative analysis. So now as we know that a compound would be made up of a cation and anion, right? So 2 parts only. So cations, we have some tests, anions, we have some others. So we put those tests. If they are positive, we get the answer to our compound, that yeah, this compound might be present there, or this anion might be present there, and that way we can find out our compound by differently identifying the cation and then the anion. Alright, so let's check out how it is found out. Alright, yeah. So now we have like host of compounds. We have lots of compounds with us, and we are given a salt. Now if we are given a salt and we have to analyze what the salt is, so one simple way of analyzing all this is looking at the colors. So the colors of the salt give away their properties also. They give away the name formulas also. So like of copper sulfate, so you'll find out that copper sulfate is blue in color, right? So it's easy to find out copper sulfate, but not each and every compound will have a different kind of color. If you have lead salts, they are generally yellowish in color, so that way you can identify some compounds with their colors but not all of them. So then that's why we need the qualitative analysis of them. We have to put some tests, and then we can find out from the chemical reactions and from the precipitates that occur and from all these substances we can find out what salt we have, right? Okay, so let's check. Firstly, for the groups, for group 1. So it's as simple. We have a salt, all right? Here we have a salt. Now I don't know what that salt is. What do? I put HCl in it. Simply. So I put dilute HCl here. Now, if the salt, if the cations present, if they are of silver or mercury or lead, these three, group 1, they'll precipitate out as a chloride salt like AgCl or Ag2Cl2 or PbCl2. So will form precipitates, right? AgCl is white in color, again lead, yellowish. So from this we can find it out. We can find this 3. So we know that at least group 1 is precipitated out. The others, if they are group 2, group 3, group 4, right, group 0, so they all will dissolve. They all will remain in the solution and they won't precipitate out. Hence, we can confirm the test for these 3 by just putting dilute HCl. Now, what is more important here is to understand that the precipitates might not occur like in a minute, in a jiffy. They might not occur in a like very fast. The reaction might be very slow, so you have to wait for the precipitate to occur, or there might take a little more time. So you have to keep your solution stand still. You can't move it all the time, you can't play with it. You have to have viable conditions, viable atmosphere. This is practical chemistry, this is not theory. So you have to take care of each and everything. So there should be no contamination, there should be not much movement around the apparatus, and the apparatus itself should be clean and should stand still for the reactions to appear and take place, and they might take time, so you have to wait patiently, right? So with that in mind, we'll see what else are the reactions for the other groups. All right, so now if I know that if the group 1 is present, then with dilute HCl it will precipitate. But if there is group 2, if not group 1, then what do? Simple. So we have already put dilute HCl and we have found that group 1 can be precipitated. What else we do is, with dilute HCl, if we put H2S, that is hydrogen sulfide gas, right? So this sulfide gas, what does it do? It forms acid insoluble precipitates now. Sulfides. Basically, the precipitates that are formed now are sulfide precipitates. Alright, like we have the precipitates occurring for group 2 with this, like copper, and then there's bismuth, right, and then there's cadmium. The others which can occur are, again, as we know, mercury can occur here, but mercury in the other form, that would be mercury in its +2 state, that is mercuric form, not mercurous. Mercurous is here, this is mercurous, so this here they will occur as mercuric. Alright, similarly we can have arsenic and everything. So what will happen is, these things will occur as sulfide precipitates and they will be acid insoluble, they won't dissolve in acid, and that's how we can test for group 2 by adding dilute HCl and hydrogen sulfide gas. You know hydrogen sulfide gas, right? That is the gas that smells like the rotten eggs, the most disgusting smell. Yes, you know what I'm talking about. That's great. So yes, the sulfide that they are formed here are copper sulfide, CuS. Similarly for bismuth it would be Bi2S3 because bismuth is in 3+ state. Cadmium same, +2 state, hence CdS. For Hg again +2 state, hence HgS. Similarly we have sulfides for tin, and then there is lead, no, not lead, sorry, there's arsenic, there is tin, there is strontium, and then there is lead. Yeah, so this becomes for group 2 analysis. All right, for group 1 it was only the dilute HCl that gave the precipitates. So these are chloride precipitates. Here now we get our sulfide precipitates, and these precipitates are acid insoluble. Okay, and this is how you can analyze for group 1 and group 2. Now what happens if in the salt there is nothing which is related to group 1 and nothing related to group 2? You add this and you get a clear solution, no PPT. Then you add hydrogen sulfide gas and you get no PPT, again a clear solution. That means obviously the group 1 and group 2 are not present there. What might be present there is still 3 groups remaining, group 3, group 4 and group 0. So let's check out for group 3 now. Okay, so now again we have the salt, right, and we have found that group 1 and group 2 are absent. So understand this, it's not that when you are given a salt then you will be given all the salts together, or group 1 will be mixed together and group 2 will be mixed together. There will be one compound, then there will not be many compounds. So with this you can actually find out there might be so either it will be a Ag salt like silver salt, or it may be like lead salt from group 1, and if that's not there then it's group 2. So in group 2 there will be only one salt like bismuth salt, or maybe it's a tin salt. It's not going to be a mixture of all the salts, although with the color differences in the PPT we can still find out that what all salts are present as they precipitate out in the reaction. All right, but there are very common precipitate is a white colored precipitate, and if that occurs then you just can't find out all the salts present inside, but at least you have the idea of the compounds, the cations that might be present. And then there are further tests which we can take place, but those are not in our standards and not at our level, so we can understand them later on in our life, but right now we can just understand how this analysis works. All right, so we have taken care of group 1 by dilute HCl, group 2 by adding dilute HCl and hydrogen sulfide gas. Now coming to group 3, what do we do is for group 3 we make the solution basic. All right, so now for group 1 it was acidic, and for group 2 it was hydrogen sulfide in a acidic solution. If these both they don't give the test positive test, then what do? We put hydrogen sulfide to the sample, but this time in a basic solution, right? So we don't add hydrogen chloride here. Now we don't add hydrochloric acid here. Instead we add ammonium sulfide. So this ammonium sulfide, this makes the basic solution, and then in that we add the H2S gas. If we add the H2S gas and if we get the precipitate out, now this time we'll get group 3 precipitates. All right, and they will be again be so these will be either sulfide precipitates or they will be hydroxide precipitates. All right, so the precipitates that occur here are S2 minus or OH minus, hydroxyl precipitates or sulfide precipitates. So here obviously again the precipitates that occur are from the group 3 like aluminium, or we have iron, and then we have chromium, then we have zinc. All right, so like zinc, for zinc we'll have zinc sulfide, for chromium we'll have chromium hydroxide, for iron we'll have ferric hydroxide, Fe3 plus, yes, here Cr3 plus, Zn is 2 plus, aluminum is 3 plus, aluminum is aluminum hydroxide. So these are the kind of PPTs, these are all PPTs, the precipitates which are occurring. Similarly we can have for manganese as MnS, that is sulfide of manganese. If these things precipitate in a basic solution of hydrogen sulfide, right, if we add hydrogen sulfide in a basic solution and if these precipitate occurs, then we can confirm for group 3. Okay, so in your exams when you're asked such questions, then you will not be given in the answer there are 4 options, then you will not be given 2 options of the same group. You'll have options from different groups, so that you can easily have the analysis, because you're not doing it in the laboratory, right? You're just doing it from your memory. Hence they don't confuse you with all the mixing up with the same group cations. Instead what they do is they put different cations of different groups in different options, so that you can choose wisely. All right, the choice is yours though. So these things, these precipitates, the group 3 precipitates, they are insoluble in basic solution. So they form a precipitate. Alright. Yeah. So this was about group 3. The last we have is group 4. Now, what we do is, if we can't find out that, if you see that group 1 is not present, and if you see that group 2 is not present, after this there is no precipitation from group 3 also, then what we have to do, we have to create a buffer. Now, in the solution that we already have, so what solution we have? We have a solution of, we have a basic solution of ammonium sulfide. Now, to this ammonium sulfide, we add a salt of ammonium sulfide, which is a phosphate salt. Basically, we're not about, yeah, we can add this, or right, we can create even a carbonate solution. So we just need to create a basic solution. Instead of this, we can put a carbonate here. That will also work as a charm. So basically what we're trying here is making a buffer, right? So basic buffer, yeah. So what do is, we put NH3 and NH4Cl together. So that is a base and a basic salt, right? So these are like weak acid and a strong base, this kind of conjugate, right? They are conjugate and they form what? A buffer. So in a buffer solution, when we add this buffer solution, if we get a precipitate now, all right, in this phosphates, right, this phosphates or in this carbonates, if we get a precipitate, we get a precipitate for phosphates. If we add the phosphates, then we get the precipitate as barium phosphate. Okay. And if in the case of carbonates, what we get is a barium carbonate precipitates. It's nothing different. Yeah, these kind of precipitates. So we have made a buffer, and in that buffer what we are adding either a phosphate salt, ammonium phosphate salt, or a carbonate salt, hydrogen carbonate salt, right? Hydrogen phosphate and hydrogen carbonate, ammonium, hydrogen phosphate, ammonium, hydrogen carbonate, any kind of salt will is not a problem. So if in these conditions, yes, you have to remember the reagents. Yes, all these reagents are important. These reagents are what will tell you if the cation is from which group. Otherwise, if you don't remember these, you won't be moving forward. So kindly remember all these. So they're very simple. Like initially it was dilute hydrochloric acid, then it was hydrogen sulfide, the gas, right? The rotten egg smelling like gas. Then there is in the hydrogen sulfide was an acidic solution. Now here the hydrogen sulfide is in the basic solution. Basic solution is made from ammonium sulfide. Now here what we have to remember, in the buffer solution of ammonia and ammonium salt, that is ammonium chloride, we add a hydrogen phosphate or a hydrogen carbonate, and that if it gives us a precipitate here, like for barium it's this, for calcium it might occur as calcium phosphate similarly, correct? And you can think for carbonate will be calcium carbonate, right? There can be strontium salts, there can be magnesium salts. If they precipitate out here, this confirms group 4. So this was all group 4. So here these are the precipitates for group 4, right? Okay. Now what happens if you identified for group 1, group 2, group 3, group 4, but you did not find anything anywhere? So then there is a possibility of group 0, that is the ammonium salt. So this ammonium salt belongs to group 0, and how to identify that? It's been done by a special reagent called Nessler reagent. So what is Nessler reagent? It is basically K2HgI4. This is what Nessler reagent looks like. So this gives the test positive confirmation of ammonium salt. What it will give? It will give a PPT, again precipitation, a reddish precipitation basically. So if you put Nessler reagent in your salt solution, that is this compound in your salt solution and it gives a reddish precipitate, it conforms a group 0 cation, that is ammonium. Alright, so this became for this is all these are all the tests for cations. So what we have is for group 1 it's HCl, for group 2 it's H2S but in acidic solution, acidic environment. Then for group 3 positive test occurs in again H2S but in basic environment, basic solution. For group 4 we have basically the buffer. In the buffer we can put hydrogen phosphate or hydrogen carbonate salt, right? Like for example we can put ammonium hydrogen phosphate, or we can put directly the carbonate. Okay, so we can put carbonate or we can put this in a buffer solution. This will give us a test for all the 4. Okay, for ammonium, the group 0 we have just studied. For group 0 it is Nessler reagent, which will give reddish PPT for ammonium. So this was all about the cations. Now let's understand what is being done for the anions. So for anions, so we saw what kind of anions we have. So what do we do? Now we are given a salt. In that salt, this is for anions now. In the salt we add HNO3. What is HNO3? It's nitric acid. Alright, this nitric acid is added into the solution. Okay, so just a few drops, not you don't have to pour it down inside it. So remember, the chemicals have to be used very carefully. They have to be used drop wise. You don't have to, this is not water, you are not pouring it here and there. These are chemicals. Even smallest parts of the chemicals will react vigorously, and hence you have to remember to take care and do this all wearing lab equipments, safety equipments, and doing it all in a very good environment where there is no disturbance, and you always have a guidance of a senior or a teacher around you, or at least you know what's going on there. Kindly do not play with chemicals because they are very harmful and they might burn you, either being acid or being base. So kindly take care. Okay, being said this, let's see what the test for anions are. So if I put a HNO3 here, the nitric acid, what it does is, so if the in the salt if I have put nitric acid, and if I get effervescence, what is effervescence? You have studied this phenomena, right? So effervescence is basically CO2 evolving. So if CO2 is evolved, what does this confirm? This confirms carbonate. So the test for carbonate is simply adding HNO3. You add HNO3, and if you get the effervescence, that means it's a carbonate salt. And if there is no effervescence, then it's definitely not carbonate. Can be anything else as an anion, but not carbonate. Okay, so you have added HNO3, but it did not work. So what do? Second thing, in the acidic solution, like you have put HNO3 already, in that solution put a little AgNO3. This is silver nitrate. Okay, so now if they have the tendency to replace this, if they some anions have tendency to replace this nitrate, what are those anions? Those anions are basically Cl minus, the halogens Br minus and the I minus. So if I put in an acidic solution of salt, if I put a little HgNO3 and we get a precipitate, so we can observe that it might have either chloride salt or a bromide anion or a iodine anion. So what is the test for chloride anion? For chloride, it's basically simply a white PPT, right? For bromide and iodide, they are generally yellow PPT. For bromide though, it is a pale yellow color. For iodine, it's actually a deep yellow or quite dark yellow color. So that way you can confirm if it's an iodide, a bromide or a chloride. White, pale yellow and deep yellow. So now You might notice in some of the books, you might see that when they get a mixture of bromide and iodide, they centrifuge it, and then by those other techniques they try to find out which one is which. But we can't do that. We don't have those kind of options in the exams, right? So obviously you just have to remember the colors, right? And with that you can find out the actual answer. The answers are quite straightforward. If you know what is going on, if you know the reagents, the answers are quite straightforward and you will remember it. Otherwise, no chance. So this is all about the game of remembering these things. Okay, moving on. So if let's say this has not solved our problem, then what do? Simply we add to the salt dilute barium chloride or a barium acetate, a salt of barium. Basically we can use anything for that purpose. We can even use barium acetate. Now with barium, if they give out precipitate, right, if it gives a white PPT, then we know it's a sulfate. Okay, so we've learned carbonate, we have learned sulfate, and then chloride, bromide and iodide. These ones are quite important. Okay, so you have to remember all of these. And then there is, okay, yes, and if we give a negative test in the solution, there is no PPT, then you can say maybe it's mostly if you add dilute BaCl2, you get sulfate as a white PPT. Yeah, if there is no PPT, then you add a little of dilute AgNO3, right? If in dilute AgNO3, again there is no PPT. So what you do? Okay, now we're just looking for nitrate. For this, the tests are quite difficult. You're not able to find nitrate. So basically just go by the negative test. How does that work? So you have added in your solution BaCl2, right? And there was no PPT, right? So what do? In your solution you add AgNO3, the one which we tried finding for the halogens. So if there is still no PPT, if there is a PPT, then obviously we have bromide, chloride or iodide. But if there is no PPT here, there is no PPT here, and there was no effervescence at the start, then obviously what it means is that we have the nitrate. It gives no PPT. Yeah. So if all the tests are negative, you can confirm that there is a nitrate salt. Okay, getting my point? So again, let us just quickly recap this part once, I mean with an example, and then we'll move on to titrimetric analysis. So let's just assume that we have AgNO3 as our salt. Now this is our salt which is given to us. So what do? So first we put, for cation we put HCl. As soon as we put the HCl, Ag being a group 1 salt will form an insoluble chloride. It will form a AgCl, and this AgCl will be white PPT, and this will confirm that Ag is present in the solution. So this was unknown to us. We put HCl in it and we got a white PPT. What does this confirm? It confirms that it's a group 1 salt. Okay, so this gives us Ag+. For nitrate, again, if we are unknown, we are trying to put in it BaCl2, there is no PPT. We put AgNO3, there is still no PPT. Right? So what do? Nothing. This just confirms that it's a nitrate. There are no PPTs. Nitrate is soluble everywhere. As simple as that. Don't worry about it. In exams, they don't ask you difficult questions from this. All you have to remember is the reagents. Okay? And for practical purposes, it's important to again note down that in practical chemistry, you have to wait. Patience is the key. Precipitates do not form in a second, a minute. They might take some time. So wait for the precipitates to occur. Check for the colors and don't don't keep moving your apparatus. Keep it stand still. Keep it on a straight position. Do not move it here and there, and your contamination should be low, and everything should be in a safe environment. You should be wearing all the safety kits, and you should be doing all this in front of a teacher or at least a known person. Okay, kindly please focus on this kind of information, because acids and bases, they can harm you very seriously. Okay, being said that, we have done cation and anions. Now let's come to our titrometric analysis. So while talking about titrometric analysis, that is simply, if we say, it's just titration. You've studied about titration, right? Titration is what? When you have acid and you base and you neutralize it, that's titration. So that's neutralization. But now what is titration basically? So again, we have an acid and a base, but now we have complete information about one of them. Like for example, if I know completely that I have an acid of some concentration and some volume, but for base I have no clue about the concentration or the volume. So then what do? How do I find it? So we have a very good tool, that is the neutralization reaction. All right, so this neutralization reaction helps us to find out if the molarity, the concentration basically of the substances. So that helps us to find out how we can calculate the concentrations with the help of these kind of things. All right, so if you want to know, for titration, you want to know how to calculate, so you have to remember a very simple formula. This is m1v1 by m2v2 is equals to n1 by n2. Yeah, or this formula can also be seen like m1v1 by n1 is equals to m2v2 by n2, as whatever is easy for you to remember. This is a ratio, and this is one quantity being equal to the other. This only means that a quantity, all the amount in the quantity 1 is equal to all the amount in quantity 2. Hence we have to have the molarity, the volume, as well as the moles. Now we'll understand what is the importance of moles and why we have requiring moles, and why can't we simply apply m1v1 equals to m2v2. We'll understand very soon. We have to see that. So I'll talk about some reactions. So we know that HCl reacts with NaOH. So this is one of the neutralization reactions you might have seen. This will give us NaCl plus H2O. Now here I see that there is a 1:1 ratio, right? So N1 and N2 are both equal. So we can just say that M1V1 equals to M2V2. But this is not the case for every solution. Example, if I have NaOH but instead of HCl, I take H2SO4. So for H2SO4 now we'll need 2 NaOH. This will give us Na2SO4 and 2 H2O. So do you see this? 1:2, the ratio, the N1:N2 ratio has changed now. Initially it was just 1:1, and that is when N1 and N2 they were not required, but as soon as it became 1:2 for this reaction, so now we require this part also. Hence this formula is very important, right? Once this formula is known, what is not is possible. Everything is possible with this formula. So think, it's given to me, let us just take an example simply. It's given to me that 1 molar H2SO4, right? 1 molar H2SO4, which is 50 ml in volume, is required to neutralize NaOH, which is again 50 ml in volume. So now what they are asking me is molarity. What is the molarity of this solution? How do I find it out? For this, first thing is reaction. Did you understand the question? I'll repeat it again. I have H2SO4. I have two things known about it, the concentration and the volume. Now I'm using this known thing to do a titration and calculate the molarity for something which is unknown. We know the salt, we know the base that is present NaOH, we know how much base is being neutralized, but we don't know what is the molarity of that base. So what do? We simply we simply do the calculation. What we do is we do a m1 v1 by m2 v2 is equals to n1 by n2. But do we know what the moles are? No, right? How do we know that? By the stoichiometry. So for this, the second thing which is important is the reaction. So what do we know? We know that H2SO4 reacts with 2 moles of NaOH to give us salt Na2SO4 sodium sulfate, right, with 2 moles of water. So now we know M1, we know V1, here is M1, here is V1, and here is N1. So this is 1 and this is 2. For 2, we don't know M2, so this is a question mark. V2, yes, we know about it. N2, we know about this 2. So now, with all the knowns and one unknown, can we calculate? Yes, we can. Simply, we'll substitute everything. For M1, it is 1 mole. For volume, it is 50 ml. See, right now I have no worries because I don't have to convert everything from here to there, because in the ratio I can cut them. I don't have the molarity for NaOH, so I'll put it as X, and here I'll put the volume, which is 50 ml. Since I have the volumes in the same unit, hence I don't have to convert them. Right? And then I have N1 and N2. The value of N1 and N2 is 1:2. So we put it like this. Now this all goes down. So then X becomes, so we have 1 upon X is equals to 1 by 2. So cross multiplying, we get X is equals to 2m, and that is the molarity of NaOH. Simple, right? So this is how we do the titrometric analysis, and yeah, that was all about the titration. One thing I would like you to note here is the main importance, is the difference between the end point and the equivalence point. Okay, now in theory we talk about the equivalence point. That is the point when M1 V1 by N1 is actually equal to M2 V2 by N2. That means all the equivalents of acid becomes equal to all the equivalents of base, not just moles. Each and every part of H plus produced from acid is equalized by each and every part of OH minus produced by base. This is what it means. Hence, when we talk about H2SO4 and NaOH, we have to take 2 NaOH for 1 H2SO4 neutralizers, because we need 2 OH minus. From 1 NaOH we'll get only 1, but from 1 H2SO4 we'll get 2 H plus. So that we'll need, for 1 H2SO4 molecule we'll need 2 NaOH. Correct? Hence we're talking about equivalence and not just moles. So this means equivalence point, and this is only achievable in theory. I mean, this is only visible in theory. We can talk about it in theory. Why? Let us understand why. So end point is actually a visible value. How is it visible? So when we do a titration, do you know how we do a titration? So basically we have a burette which is filled with the known substance, correct, and the unknown substance is put in the beaker by using a pipette, right, and then slowly we start putting the drops of the known substance in the unknown substance, so that we can measure the volume that is used for the known substance, for the unknown substance, right? So as soon as it's dropping down, so there will come a point of equivalence where everything will neutralize everything, and the effect of acid and base is cut down, but it won't be visible to us. Why? Because we have put an indicator that will only change its color after adding one more drop. So if I have HCl and I have put phenolphthalein in it, right, and now I'm going to add NaOH. So when NaOH and HCl become equal, that is the point of neutralization, and still be so initially it was colorless. At the neutralization point, it is still colorless. This neutralization point is basically the point of equivalence. But as soon as I add one more drop, the whole solution becomes basic in nature and the color changes to pink. So this point is basically a visible point, a point of change. When a color is changing or the smell is changing for the indicator, that is when the endpoint is visible, and this is what we do in our laboratories. So this is what we do in our theories, but in laboratories this is how it works. Hence the results generally that come out, they're quite little wrong, but yeah, they're still considered right, because anyways we can't reach this point in practical. In theory this is correct, but in practical we have to reach for the end point and not the equivalence point. With this we'll finish our chapter. I'll catch you soon in the next class. Okay, happy learning. Bye guys.